Okay, I think we'll go ahead and start. I have a feeling more people are going to trickle in. It's my pleasure to introduce our colloquium speaker today. This is kind of a special one because we have Professor Vitaly Kresin here. And for those of you, especially the undergraduates and graduate students in the audience, 30 or so years ago, he was sitting exactly where you are now. Vitaly was first an undergraduate here at UC Berkeley and then a graduate student with Walter Knight. And so it's kind of an honor to have him back here now giving the colloquium. And he's now a professor of physics and astronomy at USC, where he does really interesting work kind of at the interface between AMO, condensed matter, and nuclear physics that we'll hear about today. And he's garnered a number of honors, including he's an APS fellow. He's also won awards for both mentoring and teaching, which I think bodes very well for a really exciting and interesting colloquium. So thanks a lot, Vitaly, for joining us.
Well, I have to say the honor is really mine because it's very, very special for me to be here, and I really appreciate the invitation. Indeed, I was an undergraduate here from 1980 to 84 and a graduate student from 85 to 91. And I spent countless times sitting right in these very seats, which don't seem to have changed very much. Really all that I am as a physicist, I learned during my years here. So I couldn't pass the opportunity to thank all of my teachers, both present and those who are no longer here, to thank for all that they have done, not just for me, but for all my other classmates and before and after. So it really is very, very special. I have a few slides I wanted to show about my own PhD advisor that's coming up on the next slide. But in the meantime, just wanted to introduce myself and say that I'm at USC, University of Southern California. We are not to be confused with UCLA, which is the sister to Berkeley. We are a big private university, just a couple of miles directly south from downtown Los Angeles. And if you haven't visited, it's a nice campus and a nice location. And truly, Los Angeles is a very interesting city. So before I talk about the stuff which is in the title of my presentation, I wanted to mention specifically my advisor, Professor Walter Knight, because he truly was a very special person. Walter became a good friend. He was both an incredible scientist and an amazing human being, a true gentleman. He was very patient with us. He was very supportive, gave us a lot of freedom in the lab, but at the same time provided a lot of guidance and was just an all-around extraordinarily cultured and interesting person. So truly, I think it is a stroke of fortune that I got to know him and got to work with him. I want to mention, since the work, much of the work that he is known for was done right here, I wanted to mention a couple of things. Actually, the thing that first brought him to the department's attention in the very early 1950s was an effect in nuclear magnetic resonance that he discovered for his doctoral thesis that he performed at Stony Brook when he was at on Long Island when he was a graduate student. And that was a few years after nuclear magnetic resonance was discovered. He was measuring the resonance frequencies of different substances and discovered that there was an interesting shift in the resonance frequency in metals, which came to be known as the Knight shift, named after him. And it is a pretty important effect in condensed matter physics. It's a shift that arises from hyperfine interaction between conduction electrons and nuclear magnetic moments. And it's one of the most important diagnostics in NMR. Just to indicate how important it is, I plugged the words Knight shift into Google Scholar last night, and as you can see, it hit close to 2 million results. So that was his PhD thesis that brought him to the attention of the Berkeley department chair And that's how he was recruited here. Then for the next number of years, he was working here on NMR. There is still a room in the first basement of Burge that says electron microscope. The electron microscope is no longer there, but that was when he was studying his samples back in the 60s and 70s. In the 60s, there were theoretical one thing I should mention, as you may or may not know, he is also the co-author of the first volume of the Berkeley physics course, Mechanics, Kittel, Knight, and Ruderman. In the 60s and early 70s, there were theoretical predictions about interesting NMR effects in small particles. So that's what they spent some time doing, studying. And then and also at the same time, Walter was dean of LAS during the student unrest, and even told me about being locked in his office, breathing tear gas. And then he became frustrated with the fact that he could never really characterize these small particle samples well enough. And so he switched gears in the second half of the 1970s, took over an atomic beam resonance machine from LBL, I believe from the group of late Howard Shugart, and turned it into a beam to study small metal nanoparticles. And in that way, after retiring from deanship, became a pioneer in the physics of nanoclusters. Now, what are nanoclusters? These are not these things. They are rather something that is missing in this chain of materials that we're usually taught about, that we're taught things start with atoms, you combine atoms into molecules. If you combine a bazillion molecules together, you make bulk liquids and solids. If you make this kind of finite, you build nanostructures. There is a link missing for a person like me. What if, as you build molecules, you don't stop in time and just keep adding atoms or molecules one by one? This is what we call clusters or nanoclusters. So it's a clump of a finite number of atoms and molecules which are neither here nor there. And as you study them, you can try to understand how matter evolves from atomic and molecular limit to the bulk limit. And also, if there are some interesting features that are in between. And so this is what Walter was one of the pioneers in. I'll show you what they discovered. And I actually still continue to work in that field, although that's not what I'll be talking about for most of the time. So having put together a machine like this, they looked at a beam. Oh, why do you want to look at beams? Because in these cases, you can use mass spectrometry to determine how big the cluster is to within an atom. And you can also be sure that the particle you're studying is free from all kinds of external perturbations. It's not affected by the surfaces or by any kind of ligands, and you really know what it is you're looking at, which is convenient if you want to understand the basic science, the basic physics of what's going on. So having made such a machine, one of the first things Walter and his students did was to measure how many particles of different sizes are actually coming out of the source. Maybe before that, I should mention how do you make these cluster beams. So one way to do it, you have to start with vapor of the atoms and molecules, and then you have to cool it down so it condenses into particles. So if you allow me, I actually decided to bring a little demonstration, a little trigger warning, like I guess I'm supposed to. This is going to make a loud psh. This is a CO2 cartridge that you can buy in a bike store for $3.50 to refill bicycle tires. And this little nozzle that you put onto the nipple of the tire. If I don't put it on the nipple, but I simply tighten it to break the seal and press the button, hopefully you will see that there is a jet coming out until the gas comes out. So this is known as the Joule-Thomson effect. When you expand something under high pressure from a small pinhole, it cools greatly. So this thing is now really, really cold. So you saw a jet there of dry ice condensed into a beam, and also of water vapor that condensed in there. But if you use metal vapor and mix it with some high pressure inert gas and expand it from a small pinhole, you will get metal snow or metal particles. If you're dealing with a material that does not evaporate easily by heating, you can use a laser ablation to generate some laser pulses, or you can use a magnetron sputtering gun. Sputter some material that way, quench it in a cold gas, and then again you grow nanoparticles. So there are now techniques these days to grow these clusters out of pretty much any material or any molecule. So back then, back in the 80s, Walter was studying sodium clusters. Sodium is a simple metal, kind of like the fruit fly of solid state physics. And what they found was that some clusters in their beam turned out to be way more stable than others. So you can see that there are certain sizes that appear in the mass spectrum that are much more prominent than others. These became known as magic numbers. And it was Walter and his students at the time, so this was done with 3 students, Keith Clemenger, Winston Saunders, and Walt DeHere, and quickly realized that there is a strong similarity between these numbers and things that are familiar from other branches of physics, from the periodic table, where certain atoms have extra high stability, just like these clusters have extra high stability, and the same with nuclear stability. In all of those cases, this is due to shell structure. For the periodic table and for the nuclei, this is due to the filling up of quantized particle orbits in a potential well. What Walter and his students realized is that the same effect was taking place here in metal clusters. So if you imagine a metal particle, this is the positive ions, and you add conduction electrons to it, because the electrons in the particle become spread out. Even if you put together only as few as half a dozen atoms, they already start moving all throughout the particle. The electrons see a potential box. Actually, the potential of a positive ball is a standard electrostatics problem. You probably remember it gives you a harmonic oscillator. You add some electrons to this, it flattens out the bottom, but you still have a discrete box. You keep adding atoms, and therefore you keep adding electrons. These discrete energy levels get filled up. And as you add more and more atoms and more electrons, you come to cases where these shells start filling up. So it's exactly the same as the electrons in an atom, except instead of a central Coulomb potential, you have this spread out potential due to the positive charges. So this really is an effect of shell structure, electronic shell structure. And really, it was the discovery of the third case of shell structure in nature. There's the periodic table, there's the nuclear stabilities, and now there's metal clusters. And this is now even in the textbooks. I joined the group a year after they made this discovery. So therefore, I can remain modest while saying that it was really, really a great breakthrough, breakthrough. And now these electronic shell structure these clusters are often known as either artificial atoms or superatoms. Sometimes people even say that this made the periodic table go 3-dimensional because you can now choose an element and you can combine together the proper number of those atoms so as create the electronic shells that you want. So this was the time, this was what Walter Knight was doing when I was a student, and I just wanted to mention it before I go on to the next subject. Now, let me switch to the topic of my presentation, the main topic. So what we do is we start with a beam. I still work with beams, although not only with those. You pass a beam through an inhomogeneous field, electromagnetic, you deflect it, and then that tells you something about the property of the thing in the beam. I will start by talking about deflection by an electric field. Now, interestingly, that's an old subject. Actually, you will see that much of what I do really is just doing old stuff, but maybe with better equipment, which is okay, because in the olden days, people knew an amazing amount. And so their physics was such that I wish I knew a fraction of what they knew. So the first electric deflection experiments actually were done in Stern's lab, the same place where the Stern-Gerlach experiment was discovered. I'll come back to that one in a little while. In 1927, the deflection of a beam of polar molecules in an homogeneous electric field. So they were able to detect with what now to us seems like primitive equipment, beams of polar alkali halides molecules. Now, here's a little historical sidetrack that I find amusing. Even though a few years later, there was this paper that I came across that said that, molecular array experiments, they called them molecular arrays in those days, are not a very satisfactory method for the determination of dipole moments. So this was in 1931. That same person, in 1936, publishes a paper measuring the dipole moments by beam deflection. So that tells you to listen to the authorities. If you think this is just a byproduct of how they were doing those things in the 1930s, here's a more recent example. 1970s, how not to orient polar molecules. Brute force orientation is when you apply a strong field and you hope that they will orient along the field. So here is somebody writing in Science, so therefore it must be true that this is not a good way to do it. This time you had to wait a little bit longer. You had to wait 14 years, and there is a famous paper that showed that this is actually really, really good to orient polar molecules. Or there's probably a lesson there somewhere. Now, why is it actually not so easy to orient polar molecules by an external field? That's because they rotate like crazy. And as they rotate, the torque and the energy due to the external field is actually only a small correction to the rotation motion of the molecules. So basically, when a molecule is doing this, it's very hard to apply an electric field and make it orient along a certain direction. If you want to turn this into something quantitative, if you take a vapor of water molecules, the units of electric dipole moments are often expressed in these units, weird units called dBi. They're kind of like Gaussian units. But this gives you an idea of what it's like, because that's what a water molecule is like. You apply a very strong electric field. At room temperature, this additional polarization, this little shift, is less than 1 part in 100. So these are very, very tiny effects, and therefore to study them in a molecular beam is extremely challenging, and the interpretation is really hard. So how can you combat this? You can either apply a really strong field. So people have been working on using intense laser pulses to orient, to rather align molecules. And this is really cool, and there are interesting results, but you're only doing this for some hundreds of picoseconds at best. And also these beams are really intense, so that you may ionize or fragment molecules. When it works, it's great, but you want something more general. You can make these things really cold. You can put molecules in ultra-cold optical traps, which is also amazing. These are amazing, but they're limited to specific small molecules. And if you want to change the molecule, you basically have to buy another $1 million worth of lasers. Or you can use supersonic beams or buffer gas cooling, but that way you can actually not go much below a few Kelvin. And it's very hard to cool large molecules. You do not really cool vibrations very efficiently this way. And also, the cooling itself is kind of weird. The rotational temperature may become poorly designed. So all of these methods are interesting and powerful, have their own place, but I want to tell you about a more universal method that was discovered actually first at the Max Planck Institute for Fluid Dynamics in Göttingen, which was at that time directed by Peter Tönnies. And they were doing a lot of work on molecular beams. It turns out that just like I showed you with the CO2 cartridge, if you now expand pure helium gas out of a very cold, very small nozzle, it will also condense into particles, into droplets. The pressure has to be high. The droplet has to be very small. These are about 5 micron pinholes. We use electron microscope apertures. And also the nozzle has to be cold. It has to be connected to a cryostat that cools it to below 20 Kelvin. There is this funny effect in the Joule-Thomson expansion that there's something called the inversion temperature. If the opening is above that inversion temperature, then the expansion, instead of cooling the gas, will actually heat it up. It's kind of funny, but it's true. It happens with helium. If you try to expand helium at a temperature about 20 Kelvin, the helium beam will heat up instead of condense, instead of cool down. So it's because of the intermolecular potential, because you want the kinetic energy to drop when the thing expands. So it depends on where on the intermolecular potential curve your original gas is located. Now, so this way you can make this beam of nanodroplets, depending on your source conditions, pressure, temperature, and so on. These droplets will contain somewhere between thousands, or you can make them contain millions of atoms. as they come out of the nozzle, they evaporate helium from the surface, so they undergo evaporative cooling until they finally cool to a final temperature where they no longer evaporate during the flight time. And that temperature is pretty well defined. For helium, it turns out it's just under 400 millikelvin. Now, and it was also found that these droplets are actually superfluid. So this is really nice. It's nice, but also kind of challenging. Like, what are you going to do with a beam of superfluid helium nanodroplets? They are transparent. They are inert. They are weakly bound. Like, if you have access to a synchrotron source, you can ionize them. Otherwise, there's barely anything you can do. So that's not the end of the story. What they found at the Max Planck is that if you now pass these droplets through a background vapor of very low pressure, like 10 to the minus 6 torr, 10 to the minus 5 torr is already enough, these droplets will collide with these atoms and molecules. Those atoms and molecules will get stuck inside, and you can pick up one, you can pick up a bunch, and now you have something that is riding inside the droplet, and you can actually study that something. What's more, once this stuff gets picked up, its initial thermal energy and whatever condensation energy is released if atoms and molecules come together inside will be immediately released to the helium. Helium will evaporate more atoms from the surface, and within nanoseconds, everything again cools down to 0.37 Kelvin. So you end up with atoms and molecules or little clumps of matter flying inside these personal flying cryostats. One may say, why go to this trouble? Why not put some impurities into a dewar full of liquid helium? That is because nothing likes to be wetted by liquid helium. If you inject some foreign atoms and molecules into liquid helium, the first thing they will do is they will clump together. The second thing they will do is they will run off and get stuck to the wall. So unless you do something extraordinarily quickly, you're not going to end up with the sample that you want. When you shove them inside the nanodroplets, there is no wall, and they have really no choice but to just go into the middle. They sink in the middle where their van der Waals energy is minimized, except for one family of impurities I'll show you later. And now they're cold. They're broad, so they're very cold. They're superfluid, so things can vibrate and rotate inside there easily. They're inert chemically, and they're also inert electromagnetically. You can shine light inside there and do spectroscopy, which a lot of people do. And it's also broadly usable because this is not limited to atoms of simple molecules. You can shove in a whole bunch of atoms. You can shove in a whole bunch of molecules. You can put in biological molecules, organic molecules, anything you want. So 400 millikelvin is not as cold as what people who trap molecules can do, where they can go to microkelvins. But 400 millikelvin is also nothing to laugh at. The vibrational degrees of freedom all get frozen out. The rotational degrees of freedom are in the lowest states. So these are really very cold. This very cold stuff, and it's broadly usable. So it's not better, but it's different, and it's broadly applicable. And here we come back to the orientation business. The simple point here is that if you have some molecule, polar molecule like cesium iodide or water inside a molecular beam, and you apply a strong electric field, the orientation, this angle here, well, it's pretty well oriented, but not all that much. You put them in a helium nanodroplet where they cool down to 0.5 Kelvin. At these field strengths that we use, we have, well, maybe not 100%, but 90% orientation, which is already very, very strong. This is how all of that business comes together. So now we're certainly not the first ones to come up with this idea. There was especially a really powerful group led by the late Roger Miller at University of North Carolina that used this a lot. They used this for so-called pendular state spectroscopy. Turns out if you put a polar molecule in a droplet, cool it down, and then apply a strong electric field, and then do vibrational spectroscopy, then when instead of rotating, it just vibrates like this, vibrates. The vibrational spectrum collapses into one very strong peak, which can be easily resolved, which corresponds to the frequency of the molecule doing this. So this is amazing. They did really amazing stuff. But still, in order to analyze what's going on, you need to model these things, and you need to really get down into the trenches to understand what's going on. The deflection method is not better, but it's different. It supplies a direct observable. It supplies the dipole moment of the dopant. So this is our machine. I'm a bad photographer, so it's not especially impressive, but here is the source, our nozzle. This is what we call the pickup cells, where we embed things into the droplets, an electric field. Then I'll talk about magnetic deflection in a moment. Then they fly for about a meter so that the small deflection gets translated into a measurable geometrical deflection. Then we have a mass spectrometer. And the field is like this. In fact, this pair of plates was first built right here in Berkeley. Walter Knight's graduate student used this for deflection of metal clusters. I inherited that, and so we're now putting it to use in this machine. So these plates date from the early 1980s, and they were beautifully made here in the machine shop. And then the detector, since we need to measure the deflection, it turns out what we need to do, we put on a movable stage, and the entire chamber with a mass spectrometer just moves right and left, and we map out the profile of the beam. So the way we do the work is we first put a molecule into the droplet with a known dipole moment, and we measure its deflection. That tells us the distribution of droplet sizes. Unfortunately, it's not uniform. It's a distribution, so we need to know what it is. So after we've calibrated the droplet beam, then we can replace the known molecule with an unknown molecule, and then from the amount of deflection, we can determine the dipole moment. Now, here is actually a question. You probably know the answer, otherwise I wouldn't be here, but these are very heavy droplets. I mean, this is 10,000 helium atoms. So they're much heavier than most molecules. Can they be deflected? On the other hand, at this cold temperatures, molecules orient along the field very, very strongly. So the force they experience from the field gradient is also very high. So like, we didn't actually know if it's going to succeed when we tried. We're hoping it would, and it did. So here is, I'll show you what this molecule is in a second. It's a trimer of imidazole molecules. And this is the original undeflected beam. This is the deflected beam. My student found this Snickers wrapper that was just appropriate. This was actually for a football game for NFL, but it was more appropriate here. A couple of interesting notes. First of all, what this is the dipole moment of 3 polar molecules that are not in their ground configuration, but they are lined up head to tail because of dipole-dipole forces. So inside these very cold nanodroplets, you can generate extremely polar systems which are metastable but survive at cryogenic temperatures, and you can create really interesting complexes. Because this 14-15 dBi dipole moment is really enormous. The second thing is those who do deflection experiments for a living know that usually your deflections are a fraction of a millimeter. So having a deflection which is several millimeters was really a gift for us, because this is bigger than most deflection experiments. And that is because the molecules are so oriented. And then thirdly, the masses of this, we're deflecting droplets with these molecules. The droplets have 10,000 atoms in them. So this could actually be what they call deflectometry in the business of the most heavy neutral objects yet. So that's kind of interesting, that what you can do. Here is, I'll show you another example of how can this can be applied. Now, I mentioned that atoms and molecules like to sink inside the helium. That applies to everything, including C60 buckyballs. But it turns out that alkali metals do not like to wet liquid helium. This is due to the Pauli repulsion between the s electrons of helium and the s electrons of the alkalis. And helium does not wet alkali surfaces, and alkali atoms do not like to go inside helium. So if you collide them, they will actually stay on the surface inside these dimples. And people do high-resolution spectroscopy on these things, and it's really interesting. There was a theory paper. There were some computations, very detailed quantum chemistry computations, many pages in the journal, that suggested that if you put C60 and an alkali atom or dimer on the surface, the dispersion forces between them are going to be strong enough, the induced dipole-dipole force will be strong enough that they will actually combine, and there will be charge transfer from the alkali to the C60, and you end up with a huge dipole moment. So we decided to do such an experiment, not with cesium, but with sodium, which is actually even a better candidate than this. So C60 with 1 sodium, 2 sodiums, 3 sodiums, 4 sodiums. You don't need to do any calculations. You don't need to do any theory to see that there is no deflection. So there's absolutely no charge transfer. These things actually do not combine, which is actually kind of neat, because without doing any detailed theory, we immediately killed a long calculation. And I don't want to be too glib, but experimentalists like to confirm theoretical predictions, but they like even more to kill those. And so here's with one measurement, the entire prediction was destroyed without actually, as I said, without doing any calculations. Just to show you that it's not universal, here is C60 with ytterbium atoms, and there is a clear deflection. If you calculate the dipole moment of the ytterbium atom over C60, it turns out that it likes to be over a pentagon face, and what we measured was exactly what our theory scholars calculated for this combination, which also has an interesting implication for the bulk, because it turns out that this is exactly a configuration that ytterbium C60 acquires in the superconducting bulk phase. So this is just a small building block of this fullerene superconductor. Here's a couple of examples of things that I would like to keep on studying with electric deflections. I'll just to let you know what kind of things you can do. I would like to put amino acids in there. Amino acids are dipolar. They combine and form dipole and form polar structure. I would be curious to see how putting a couple of 2, 3, 4 polar amino acids compares with polypeptides that are already preformed and dipolar, that can give us some ideas about the molecular steps of the assembly of peptides. Another thing that's interesting to try is to study what's called photochromic materials. These are molecules that under illumination turn from symmetric nonpolar to asymmetric polar things. And here they are transparent, here they are colored. It's actually the same stuff that you find on sunglasses that turn dark when you go out in the sunlight. They have these molecules that turn under the influence of sunlight, turn into colored. So I want to put those into nanodroplets, shine light on them, and discover how from non-deflected they will go to deflection. I think that's going to be kind of a neat new type of spectroscopy. So this is about electric dipole moments. Now, the next thing I want to talk about is magnetic deflections. Now, until a few years ago, I was never doing magnetic deflections. People studied magnetic clusters, and there's some very interesting properties of those. I was never really going to get into it because it's technically difficult. The results, the interpretation of the results is very, very sensitive to what you know about the temperature of the cluster. And at conference, people would always be at each other's throats saying like, no, you did not measure your temperature correctly. No, you didn't measure your temperature correctly. So I didn't want to get involved. But as you can see in these nanodroplets, I don't have to argue about whether I know the temperature or not. The temperature is 0.37 Kelvin. So, and nobody else was doing this. So sort of, even though I still don't understand spins all that well, they're really confusing, we kind of felt like we should do it. So also, as it happens, it's kind of appropriate that we're not very far from 100th anniversary of the famous Stern-Gerlach experiment. And as I said, we're just still doing the same thing 100 years later, just with different stuff. And it's amazing what they were able to do. So Otto Stern was definitely one of the most remarkable physicists of the 20th century. A couple of things I want to mention about him. First of all, in some reminiscences about him, I found this quote that my graduate students really, really relate to. So just like in our lab, we can never get any signal going anytime before midnight. The second thing is, people might know it, but I actually did not know that until I already left Berkeley. Otto Stern, of course, was sort of one of the great figures in atomic physics, so the inventor of the molecular beams method. His laboratory in Hamburg was legendary. In 1933, he had to leave Nazi Germany and move to the United States. For about 15 years, he worked at Carnegie Mellon University. And he did some work there, but he never really kind of was able to regain the same stature and the same power as before. And of course, his Hamburg lab decayed. So as we know all very well, it's much easier to destroy things than to build them up. So in 1947, he retired from Carnegie Mellon, and as a matter of fact, moved to Berkeley. His sisters, and then one remaining sister lived here. And from 1947 to 1969, he lived here in Berkeley. I actually traced where it was. There's the address. There's Marine Avenue. There's Tilden Park. So it was this house right there. It still exists. This is from a current real estate photograph. And he would regularly come to this very colloquium, apparently. And I don't know if anybody here met him, but it's kind of remarkable. So there's all these connections. I don't think he had Pete's Coffee at that time. So this is our machine that I already showed you. What we added now is a Stern-Gerlach magnet. Actually, it's the so-called quadrupole sector field. Often in this business, people use electromagnets, but following example of somebody from Stanford in the 80s, we realized that we could actually do the same thing by using very strong permanent magnets. So we can actually build a permanent magnet that is much based Stern-Gerlach deflector that is much more compact and much cheaper than an electromagnet. And it has the same kind of strength and gradient as those. And here is a requisite picture. This is my graduate student installing the chamber and aligning the magnet, because everything has to be aligned to a few tenths of a thousandth of an inch. So he spent a good number of weeks with his surveyor's telescope, making sure everything in the molecular beam thing is aligned. And then it worked. So let me show you a few examples of what we saw. So I already mentioned these alkalis. So the alkalis don't like to to go inside the helium droplets. They sit on the surface. What happens if you put two atoms together? They find each other. They wander around the surface. They find each other, and they bind into a dimer. Or if there's three of them, they bind into a trimer. Now, if they bind into a ground state system, which is, for example, for a dimer, it's a singlet, opposite spins, there's a lot of binding energy that's released. And in that case, they boil off from the surface, and you don't see them. So it was already in the 1990s that people discovered by spectroscopy that when you populate these helium nanodroplets with alkali dimers or trimers, you end up not with ground state molecules, but with high spin systems. So for the dimers, it's triplets, and for the trimers, it's quartets. So this is not new, but this was a good test system because we could make this thing. And indeed, it deflects. Now, this is a very, very weak signal. We have to collimate the beam to a small fraction of a millimeter to resolve these deflections. So our counting rates are usually about a few, maybe like 5, 10 counts per second. So these measurements take a long time. This was one of the most difficult ones because the signal was very weak, but it was enough to measure the deflection. So magnetic deflections also work. And again, this is not something that was seen for the first time, but from just one direct measurement, you already see that the dimers that are formed on the droplets are not singlets, but triplets. So they're in the metastable state. Again, the beauty of this thing is that some observables you can just see directly by looking at the data. And of course, it also shows that the experiment works. So then I was looking for something that would have a strong magnetic dipole moments, and was looking for some old textbooks and realized that there are these textbook paramagnetic salts that you find in all kinds of introductory textbooks in the chapter on paramagnetism that talk about these crystals. So for example, there is this crystal, ferrous chloride. In this case, the iron gives away its 2 s electrons to the chlorines and just remains as a doubly charged iron cation. This is its configuration, and the ground state has this spectral character. Now, if you look in the solid state textbooks, they tell you that if this entire angular momentum went into the magnetic moment, you would get this much of a magnetic dipole measured in a magnetic susceptibility experiment. But we measure something much smaller. And what you measure is actually very close to the case as if only the spin gets magnetized. So this is known as the quenching of the orbital angular momentum. Electrons cannot easily spin around due to the presence of the crystal field. And so the magnetic moment in these crystals is due to spin only. So we put them into our nanodroplets, and we saw a strong magnetic deflection. And one interesting thing is that the fitted magnetic moment was this much. If you look at the table I showed just before, it's exactly what you already see in the bulk. It's actually kind of interesting with these molecular and cluster experiments. There are certain features which are often described as due to the crystal environment that are in fact somehow transparent already at the molecular cluster level. You shamelessly extend them down to very small dimensions and they still work. So this tells you that even in the single molecule, the orbital angular momentum is already quenched, which for one thing means that the molecule must be nonlinear. Otherwise, there would be the projection of the angular momentum would be a good quantum number, and that is not the case. And there are a lot of calculations that tell you that this molecule is linear, and this one experiment tells you it cannot be linear. So this is kind of things on the molecular level. Now, this tells you, this deflection tells you that the molecular magnetic moments are thermalized. So on the one hand, this is a big advantage over isolated clustered molecule measurements because, as I said, we actually know the temperature of these spins. We also know that the transit time through the magnet is about 300 microseconds, the way the beam flies. So the spin relaxation thermalization time is much less than that. And then comes the interesting fundamental question. How do these spins actually thermalize? It's a pure helium-4. There's absolutely no magnetic impurities or magnetic moments anywhere. So how does the thing thermalize? Now, I'm told by my colleagues who do electron spin resonance that in crystals, the main relaxation channel is by the spin-phonon interaction. But in this case, it's just one molecule. Its vibrational energy is way more than Zeeman energy, and these vibrations are frozen out anyway. So it's not that. So that's kind of an interesting fundamental question. So what it has to be, I think, is spin rotation coupling. The molecule rotation interacts with the helium, becomes thermalized, and then the spin interacts with the rotation of the molecule, and by spin orbit coupling gets somehow thermalized by this two-stage process. The spin rotation coupling contains of two parts. One is just simply the negative chlorine ions spinning around the nucleus are kind of like a current loop. So there's an interaction with a spin magnetic moment, and that is one interaction. And then another one is Van Vleck in 1951 showed that you can do something called the Van Vleck transformation that converts the interaction, the spin orbit interaction in an atom, into a form that can be presented as the interaction between the spin and the molecular rotation. Reading these papers have massive matrix elements like this. Reading these papers made me realize several things. One is that Van Vleck was a genius. The other one is that I definitely am not. And the third one is that we physicists really should be taught much more molecular physics than we usually are. There is more to life than just atoms. Molecules are amazing, and I wish I knew more about how to do all of those matrix elements. People used to know it because one of the papers with Van Vleck was actually written by Charles Towns on this very stuff. So people used to know how to treat molecules. One thing that is annoying, though, is that these amazing papers tell you how the energy levels get split and all kinds of characteristics. But if I want to know the rate of thermalization, I need to know the coupling strength. And then you read in the textbooks, there's like Hund's case A, case B, case C, and so on. I want to know the strength of the coupling because it's going to give me the transition rate. You go to all these papers, they put in front of this a coefficient that they call G, and they say it's a coupling strength to be determined from experiment. Not super helpful. But I think this is a really interesting fundamental question, and there are actually there's no theoretical work in actually calculating exactly how this works, exactly how this relaxation works. Here is a case where this has some relevance to condensed matter. We don't have to put in only one molecule, we can put in two. That creates dimers. It turns out that a dimer has no deflection whatsoever, so that tells us right away that the spins in the two molecules together point in opposite directions. We can make trimers. We clearly see that they're antiferromagnetically oriented because the measured magnetic moment of this trimer is to within the error bars is the same of a single, so it has to be like this. And this actually kind of goes into the realm of how do you build crystals. So we have antiferromagnetic spin orbiting. I'm told by some theory colleagues who are calculating this stuff, that's interesting. In order to explain why this ground state configuration is low spin, you have to include electron correlations or some kind of Hubbard terms. Otherwise, you will never get this result. So that's kind of interesting for many-body condensed matter physics as well. And in general, the evolution of this magnetic ordering as you add more and more pieces together is interesting from the condensed matter angle as well, because these are very interesting materials. It's been known that below the Néel temperature, they have ferromagnetic interplane coupling, antiferromagnetic interplane coupling. They have field-dependent susceptibility, something called metamagnetic, which I had never seen before. It turns out already in 1935, Landau was writing papers trying to explain how these very crystals react to the magnetic field. And so in a way, here is a recent paper that appeared last month. You can kind of ponder how the magnetic moments of these things go from the molecules and dimers and trimers that we study all the way to monolayers. So there are some interesting implications about this bonding and this bonding. So that's the way in which what we do also has relevance to condensed matter physics. And they also predicted some very interesting high-spin assemblies that can be produced, and we plan to test some of those. Now let me go to the very last part. There's just 2 or 3 slides left. So we all know the Stern-Gerlach experiment. This was actually a test of our magnet that was done by a colleague of mine in Germany. We shipped the magnet there. They passed a beam of bismuth atoms through it. It's a 3/2 system, so it's the beam splits just like in textbook into 4 beamlets according to the 4 projections of the angular momentum. And then the question is, if we were to put this into a nanodroplet, will I get this Stern-Gerlach splitting, or will I just get a uniform deflection? On the one hand, the helium droplet is a heat bath, so these things should become thermalized. On the other hand, how would they become thermalized? There's no magnetism inside helium nanodroplets. There's no molecular rotations, so maybe they should behave like this. And actually, before we did the experiment, nobody could tell me because it was never done. Turns out they deflect one way. They somehow become thermalized. So this is an experiment on a couple of high-spin atoms that we put in the nanodroplets. They all deflect one way to the left. So this means the spins actually somehow become relaxed and they thermalize. Now, that's the good news. The bad news is here is the fit to the magnetic moments which we are measuring. If you look at these numbers here, this is not what we should be seeing. We should be seeing 3 Bohr magnetons here and 7 Bohr magnetons here instead of this. The one thing that we had in mind was like, see, what is the effective spin temperature? Like if it's obviously not 0, but it's somehow reduced. If you do the spin, you find that the effective spin temperature is a few Kelvin. So the spin does get relaxed, but it doesn't have time to relax all the way. So the vapor was at 500 Kelvin, the nanodroplet is 4 Kelvin. After about 300 microseconds, the spins are at about this temperature. So that is kind of intriguing. But they do somehow relax. And that is actually also one of the big puzzles that I want to finish my talk with. How does this relaxation even proceed? As I said, helium is completely non-magnetic. This time it's just a single atom. There are no rotations. There's nothing to couple to. And yet somehow spins are able to give their, Zeeman energy over to the helium. Again, there's no theory about it, which is too bad. I know one theorist in Austria who does this kind of stuff, but he's got too many projects on his plate, so he's too busy. But this is my only idea. So what can interact with the atom is the atom sits inside a cavity inside the nanodroplet. The cavity's walls jiggle, and there are rotations. It can interact, in principle, with the angular momentum of the atom. Because after all, the atomic orbitals in these complex atoms are not completely spherically symmetric. So the atoms can jiggle, they can interact with the helium excitations. And conversely, so the helium excitations can cool the atomic orbital motion. Then somehow, via the spin-orbit interaction, this can produce a channel for thermalizing the spin. It's purely hand-waving. I don't know precisely how, but an interesting thing is there's actually an analogy with the famous Einstein-de Haas effect, which is over 100 years old, which tells you that since spin is a real angular momentum, if you take a demagnetized piece of matter and then magnetize it, align all the spins, there's actually mechanical rotation that can induce in the sample. So there is a transfer of angular momentum between spins and the physical orbital motion, which is pretty much what we have here. And an interesting thing is, again, I am told that even though the effect is old and recognized, there is actually no microscopic theory that clearly describes how this goes on. So this is really a very fundamental question, interaction between spins and surrounding matter. And so if anybody is interested in trying to tackle this, by all means, because I think this is kind of curious. Right now, I kind of find myself in a position of this. I was in Munich a few years ago, and they have this amazing science and technology museum, probably the greatest one in the world, called the Deutsches Museum. One of the things they show there, as you can see, there's a 1912 model explaining the Zeeman effect. That's not quite how we understand it right now, but with these experiments that I describe, I'm sort of finding myself in the position of staring at something like this and trying to understand it. So what I try to describe to you is that in this sort of nanoscale system, this is a playground where we can explore magnetic and electric polarization of things, and it covers the range all the way from some fundamental atomic physics all the way to condensed matter physics and molecular physics in between. So it's really a very interesting area to play with. And so in the end, I just want to thank my former students who put this together, 3 graduate students who put this together, 2 undergraduate students. We had a visitor from Innsbruck who spent several months in the group and helped us a lot, and my 2 current graduate students, and thank you very much for your attention.
Thanks, Vitaly, for a really interesting talk. We do have some time for questions. Okay, maybe as the host, I'll use my prerogative or whatever to ask
or
the first.
Or your obligation. Yeah.
Yes, so our obligation, sure. So this is actually very basic. Maybe I missed it, but when you have a permanent magnet, how are you taking the 2 curves where you show magnetic field off versus magnetic field on?
That's a very good question. My initial thought was that we could just use the pure helium beam to use as the undeflected thing. And that turned out to be not accurate enough. So we're now doing it in a very primitive way. We have the thing mounted on shafts, and we just move it in and out. And I didn't expect it, but with a good enough machine shop, you can actually have the whole thing reproducible to better than 1/1000 of an inch. It just goes up and down.
Okay, other questions?
Uh-huh. The deflection chamber, we don't need to move. We just move. The magnet is sitting on mass spectrometer. It's on a rail, sort of with bearings. It's connected by a flexible bellows to the rest of the machine, and the rail is moved by a stepper motor just very accurately back and forth. So it actually works. Originally, we just wanted to put a slit in front of the mass spectrometer and just move the slit with a stepper motor like this. And then, this is kind of interesting. That's what we did. And we found that we had a deflection. But somehow, the intensity of the deflected beam was much weaker than that of the undeflected beam. And I couldn't for the life of me understand why. And I came up with all kinds of crazy things. After a while, we actually realized the reason was that the deflection was so big that the beam was actually missing the entrance to the slit. So that was the only time in my life where my estimate was actually ended up being more pessimistic than the result. Usually you end up being worse than you expect. I think I used up all of my good luck on that one experiment. The effect actually turned out to be about a factor of 5 stronger than I expected. Then we realized we cannot just do this. We have to put the whole chamber on rails and move it back and forth.
How does the superfluidity of the helium affect and work with the dynamics of the motion of the particle or molecule inside?
Thank you. So for us, for what experience I showed, all it pretty much needs to do is to enable the thing to orient itself without any viscosity, any friction in the direction in which we want it to point. That's kind of all we need. It probably also has implications for spin relaxation and so on, but that's hypothesizing. A lot of people use these systems to do high-resolution spectroscopy because they can put various molecules in there. They become very, very cold at the same and the only other way to make molecules this cold is to put them on a cold substrate, but that usually really interferes with the vibrations, the rotations. Here, nothing. So people can study very high-resolution rotational spectra, for example, due to the fact that molecules can rotate freely, and also with the vibration. There are some interesting effects. For example, the moment of inertia of molecules you measure in these droplets is actually different from that of a free molecule. And hand-wavingly, this is explained by saying that the molecule drags some helium around. But somebody also put together a microscopic theory that says basically you can explain this as the molecule exciting rotational quasi-particles in the superfluid helium. So for these kinds of spectroscopic experiments, the fact that it's superfluid is really important because otherwise you would just get big, poorly resolved blobs in your spectra instead of high-resolution effects. And then, of course, another thing is when we put together complexes, like several molecules, they approach each other and they align according to the dipole moments. I think if this thing were not superfluid, they might get stuck in some configurations which are not so interesting. Here, they can really just follow whatever their multiple moments order them to do. Mm-hmm. Oh, sorry, there was a question up there. Yeah.
Why do some molecules equilibrate inside the droplet and then the alkalis on the outside?
There is it's basically a balance, the way I understand it. It's basically a balance between the Pauli repulsion, between the s electrons of helium and alkalis, as I mentioned, and the van der Waals attraction between helium atoms and the impurity atoms. And if you write down a balance between these two, there is a certain dimensionless number that comes out, and that was sort of done already some time ago. And if the number is less than 1, that means the repulsion wins. And if the number is greater than 1, then it means the attraction wins. And so it turns out that if you put in sort of the polarizabilities and the repulsive parts of the Lennard-Jones potentials, the alkalis end up on the non-wetting part, and the other atoms end up on the wetting part. So that's sort of the approximate idea. So it's again, it's a competition between attractive forces and repulsive forces.
Maybe one more question. Yeah.
So I don't want to sound like the people in the conferences, but when we think about this thermalization of the magnetic dipole, like you fitted this curve to around to be representative to 4 kelvins.
Right.
How do we know that this atom reached the thermal equilibrium with the droplet? Like if the tube was longer, would it lower in temperature?
So there's two parts. For the molecules, it seems like they thermalize because if you want me to give you a absolutely bulletproof argument, I cannot really do that. But what I can say is if I measure a magnetic dipole, which is identical to what people measure in a crystal, it cannot be a coincidence. So they must have thermalized. For the atoms, as you can see, the magnetic moments that we measure are actually not thermalized, and they're not what you would expect for a free atom. They're somewhere in between. So that is sort of says that no, I'm not, in this case, I'm not claiming that they become thermalized. I am claiming that to a certain degree, the Zeeman energy was given over to the helium. And I'm completely puzzled about two things. One is, how does that happen? And number two, why is there no time, not sufficient time to have it done completely? So there's just no microscopic explanation of any of those. And I think it's kind of intriguing.
All right. Let's thank Vitaly again.
Thanks very much.